Good morning, Dr. Ajay and my fellow classmates. My name is Nigel from Group 14, and I'm joined by Trayshawn, and today we want you to meet Blackpink, our robot that will be competing in next week's competition. Before diving deep into Blackpink's uniqueness, here's our presentation outline. First, we will go through Blackpink's purpose and its solution approach. Secondly, we will be going through key innovations in Blackpink's design. Thirdly, we will be going through the implementation details and competition strategies. Finally, we will go through alternative designs we explored but didn't finalize. Now we will go through the system overview of the robot. Blackpink's system integration comprises three main blocks. 1. Color sensing or puck manipulation, CSPM. It uses color and IR sensors to detect the right puck color and activates the gripper. 2. Locomotion. It handles movement, collision avoidance, and alignment. It also utilizes motor-controlled wheels, shaft encoders for distance tracking, sharp sensors for front distance measurement, and ultrasonic modules for alignment. 3. Power line. It uses 16 batteries which powers the 12-volt line which has been stepped down by the DC buck converter to obtain the 5-volt line. Now we are going to go through Blackpink's robot design and structure. Blackpink's gripper, a primary innovation, boasts several notable features. 1. Ground clearance. The retraction ensures the gripper activates only for the correct puck when the correct puck color is detected, which will enhance ground clearance efficiency. 2. Power efficiency. By disabling the gripper during inactivity, it conserves energy, enhancing robot runtime. 3. Safekeeping mechanism. Its retractable design safeguards against external damage. Further details will be discussed in the mechanical structural section. In the traditional backtracking method, if a robot discovers a puck during its scan, it retraces its entire path to return to the base. This becomes highly inefficient for longer scan paths. Our approach allows the robot to take a shortcut back to the base once aligned, eliminating unnecessary backtracking and speeding up the return process. The conventional backtracking method employs the following strategies. 1. Exploration strategy. It searches the entire solution space until a solution is found or the path is deemed unsolvable. 2. Pruning. This method often explores unpromising paths due to inefficient pruning techniques. 3. Completeness. While it guarantees a complete search, it may be time-consuming. Blackpink is a product of innovation and is no doubt a multidisciplinary project, mainly software, electrical and mechanical engineering. Right now, we would like to share with you the crucial aspects of our design. Let us start from the software side of the design. We prioritize code modularity for its reusability and clarity. We utilized a finite-state machine approach for Blackpink's functionalities, defining its actions in 16 streamlined states. FSMs grant us greater control, prevent unwanted functions, simplify debugging, and facilitate the addition of new functionalities without overhauling existing code. For a straight-line steering strategy, we applied a proportional controller, setting the slower wheel as the master and adjusting the slave's PWM based on encoder feedback. By tweaking the proportional gain, we found the ideal balance to minimize path deviation and oscillations for optimal robot correction. Our route planning leverages a predefined raster scan pattern. Blackpink aligns itself after each row during the scan due to accumulated turn errors. A navigation stack logs its position and direction, aiding in localization and backtracking. If a puck is discovered, the robot determines its arena side, possibly using the stack to redirect itself efficiently back to base. Let us continue on with the power management and electronic side of the design. We prioritized efficient energy consumption. We implemented a buck converter for a more current-efficient 12-volt to 5-volt conversion than traditional voltage regulators and established two distinct power lines for safe, organized connections. To conserve energy, we deactivate high-power components like color sensor LEDs and gripper servos when idle and optimized our backtracking algorithm for direct returns, minimizing wasted motion. We optimized sensor placement for precise detection. Both color and IR sensors are centrally positioned at the robot's bottom, ensuring the IR detects pucks directly beneath the color sensor for instant recognition without gripper interference. While initial tests showed varying detection rates for different puck colors, surrounding LEDs with black tape focus light downward, boosting our detection accuracy to 100%. Our main focus is simplicity and precision. We've fitted the robot's rear with limit switches, prompting it to reverse until it contacts a wall during alignment. This positions the robot optimally towards the puck collection zone. Though this takes extra time, we prioritize alignment accuracy over speed for enhanced navigation.
Finally, I will be talking about the mechanical structure side of the design. The robot's weight distribution is crucial. To prevent uneven power usage, the heavy and motion-related components are placed at the bottom, ensuring a lower center of gravity and minimizing power waste. The PSOC, sensors, and batteries are on top for easy debugging and programming access. Here is our funnel design. Another design feature is a narrow funnel underneath, allowing pucks to slide through without affecting sensitive areas like motors. This ensures pucks are organized for potential future detection. Here is our gripper design. The puck capture system uses a dual-parted gripper with a servo motor for each section. Unlike older designs with interlocking gears, the servos connect directly to the gripper base, enhancing torque. The gripper arms have an interlocking gear structure with dual gears at a 19.5 degrees angle, ensuring steady contact and swift, precise movement. A top covering retains pucks even with the PWM servos off. This is the design of the flicker for our robot. 1. Simplicity is key. We've made our puck flicking mechanism intuitive. 2. We prioritize seamless integration, ensuring the flicking mechanism complements the puck handling and detection seamlessly. 3. Cohesive performance. Every component is designed to function harmoniously for optimal performance. 4. And a unified control, a single interface to control both puck handling and flicking. Our decision-making process can be divided into 3 consecutive stages that prioritize 3 goals, which we would discuss. The project also has 3 priorities in ascending order of importance. We will start by discussing on the priorities and focus. The robot design emphasizes most of the accuracy, safety, and robustness of implementation as shown by the puck detection, gripping mechanisms, and the USM alignment. When we have decided that the accuracy and robustness is met, we would focus on programmer controllability, as shown by our implementation of the finite state machine for a more controlled operating system and navigation stack for a more controlled localization system. Once both priorities are met, only then do we prioritize optimality and efficiency as shown by the implementation of the backtracking shortcut algorithm, IR and color sensor placement. We will now go through the decision flow. Before we decide on 2 alternative implementations, we will first evaluate our project priorities, which I have stated previously. We would then evaluate its accuracy, followed by its optimality and efficiency when put on the arena, before actual testing and validation on the arena. Now, I will be going through the alternatives and what design we ultimately went with. We weighed the solenoid approach against the base flicking mechanism. The solenoid required a dedicated power source, which was costly, complex to integrate, and had a lower durability. In contrast, the base flicking mechanism was energy efficient, cost-effective, simpler, and more durable. Our choice: the base flicking mechanism for its smart and efficient design. Now, comparing the limit switch and the ultrasonic sensors, the former had limited range, less precision, and was prone to wear and tear. The ultrasonic sensors, however, offered extended range, superior precision, non-contact sensing, and adaptability. Our decision? We chose the ultrasonic sensors for their superior sensory capabilities. So, finally we have reached to our conclusion. In summary, we covered the problem statement, how Blackpink aims to solve it, how it stands out from the crowd, and our thought process when designing Blackpink. We hope you enjoyed our presentation as much as we did create Blackpink. Thank you very much for your attention. We're open to answer any questions you might have.